Hi class, it's Dr. O, and as promised I was going to go over some homework problems from the homework set to make sure that we have understanding of what's going on here. What I'm going to be looking at is from our most recent homework set, which was a homework set from an MIT class for Organic 1 in 2005. What we're going to be looking at is problem 5, starting with C and going through the end of the problem, which is F. So to get started, let's start with C. This is problem 5, C. And the stated question is, starting with this molecule right here, to treat it with Br2 and H2O, what are the products of this molecule with all stereochemistry involved? And the question further states that for all of these questions, C through F, state whether the products are optically active, optically inactive, due to the fact that you're forming two stereoisomers, which are going to happen in 50-50 ratio, which would be a racemic mixture, or whether the product form is optically active due to the fact that it's meso. And the three symbols that we have for this are C for optically active. C stands for chiral. Optically inactive due to forming a racemic mixture, which will be designated R, or optically inactive because you form a meso compound, and the designation for that will be M. So if we look at the product here, the first thing that we notice about this reaction is we're treating an alkene with Br2 and H2O, and immediately what we get from this is we're going to form a halohydrin, and a halohydrin is going to form putting the halogen at the least substituted position and putting the OH eventually at the most substituted position. This is considered to be Markovnikov, and the stereochemistry of the two is they will be trans to one another due to the formation of a bromonium ion intermediate. The other thing that stands out about the starting material is the fact that we are beginning with a molecule that is already chiral. This carbon right here is chiral, and we have established stereochemistry here. Due to that fact, we're really going to think that the product we're going to form is chiral. Now, we are going to form a trans product here, but we're going to get a mixture of two trans products, and what's going to happen is the stereochemistry here is going to form a racemic mixture of two stereoisomers. Well, except for here we have two methyl groups, so it looks like we're going to form one new chiral carbon. The problem is the new chiral carbon, we're going to form some of it in one configuration, like S, and we're going to form some in the other configuration, say R. However, what we have here is we already have a chiral molecule, and our reaction is not going to touch this. So let's see what we get. I'm not going to draw through the mechanism here. I'm just going to draw the product. So here we have our backbone. We have our chiral methyl group here, or our chiral carbon here, due to that methyl group. And I'll draw the backbone here, and now we have a methyl group up here, we have a methyl group up here. We're going to put a hydroxyl group with one stereochemical designation here, and we're going to put the bromine here with the opposite configuration. So that's going to be a bromine. And that is one product that we make from this. And we notice that if we figured out our stereochemistry here, that's a methyl group coming out, which means we have a hydrogen, I'm sorry, the methyl group going in, the hydrogen's coming out. If we do our stereochemistry here, where we see that this is the fourth highest priority, this is the highest priority, this is 1, this is 2, this is 3, which way is the car turning, so to speak, we see that the stereochemical configuration at this chiral carbon is R, and the stereochemical configuration of this one, if I was to draw this H coming out, is, well actually let's look at it in just a second. Let's look at the other product. We can get the reverse of these two, and I'll show you why I did not established the stereochemistry yet because it'll be much easier to do it for the second one. Actually, this is supposed to be going out, OH. And then here we're going to have the bromine coming out. We're going to have the hydrogen going in. Here we have the hydrogen coming out. We have the methyl group coming in. That's a chiral carbon. This is a chiral carbon. So our substituents priorities are going to be the bromine is going to be the highest priority. So we're going to give that the number 1. And then if we look over here, we have a carbon off this substituent. We have a carbon off this substituent. This carbon outweighs this one. So this one is going to be 2. This is going to be 3. And which way does our card turn in this case? We go from 1 to 2 to 3. Well, this is S. This is S. So this one right here is going to be R. This is going to be S. That makes this one R. So we have a mixture of R, R, and we have a mixture. We have a mixture of RR and RS. And the question is this molecule chiral? And the answer is absolutely. This is a mixture of diastereoisomers, and there you have it. It's chiral. These two molecules are going to have different chemical and physical properties. They are not enantiomers of one another. So that's the answer for B. This reaction is called the formation of a halohydrin. A trans relationship between the halogen and the oxygen goes to the more substituted carbon. Let's move on. Let's look at D. D. The stated problem is this molecule, and it is treated with OSO4, osmium tetroxide. That's the first step. And in the second step, we treat it with hydrogen peroxide, H2O2. And the product that we get from osmolysis is a cis-vicinal-diol. And here's our cis-vicinal-diol. We're starting with the trans alkene, and we're going to get the OH adding to the same base. Plus this. Although it does appear that this looks a little sloppy how this is drawn, because we see that these are both sp3 hybridized carbons, and it might be nicer to draw them as tetrahedrons or closer to a tetrahedral representation. You're going to find that in synthetic organic chemistry that it's drawn like this quite often, because this clearly shows the stereochemistry involved. And what we're going to have here is we can solve our stereochemistry here, and we're going to find out that we're going to have a mixture of SS and RR. These are enantiomers of one another, and the definition of, or at least a way to describe enantiomers is if you have more than one chiral center, all the chiral centers have to be opposite. And what we have here is two chiral centers, and in each case they're opposite. This is a racemic mixture, so it's going to be designated R. Up here, this one is going to be designated C. Okay, let's